I'm Sergey Legtchenko from Microsoft Research, and I'm going to talk about Pelican, which is our building block for Exascale cold data storage. So first of all, what is cold data? Cold data is data which is written once and read rarely. We believe it represents a significant fraction of the data stored in the cloud, and therefore we really need to make sure we store this data efficiently. If we look at storage technologies available today, every technology makes a specific trade-off between cost and latency. For example, SSDs are quite expensive but offer very low latency. Then we have enterprise disks that are slightly cheaper and slightly worse latency. Then we have commodity disks, and finally tape, which is extremely cheap but offers latencies in many minutes to many hours. So because of this specific trade-off, every technology is naturally well suited to store a particular type of data. For example, SSDs in enterprise are perfectly suited for hot data, which has very tight latency requirements. Commodity disks can be used for slightly cooler but still warm data. And finally, tape, because of its very high latency, can only handle archival workloads that are composed of data which is virtually never read. So what about cold data, which I told represents a large fraction of data stored in the cloud and is still accessed from time to time? Well, tape cannot handle it because the latency is too high. And in fact, none of the technologies available today offer the perfect trade-off between cost and latency that is the best for cold workloads. So what happens currently is that cold data ends up being in the hot or warm tier, which is provisioned for peak performance, offer high throughput, low latency, but is very expensive. And this is not an efficient way of storing cold data. So what we would like to have instead is a cold tier that would offer storage density and cost similar to tape, but at a much lower latency. And this would enable it to be flexible enough to handle both archival and cold workloads. And that's what Pelican does. If it's compared to tape, it offers better performance in terms of latency at a similar cost. And this is achieved by right provisioning. By right provisioning, we mean that we provision resources in the system just enough to satisfy the requirements of the cold data workload. For example, we designed the system for archival and SMR disks instead of commodity. These disks are optimized for spin-up cycles and capacity, but not IOPS. We do not provision power, cooling, and bandwidth for all disks to be active concurrently. Instead, we provision just enough of these resources so that there is enough disks active concurrently to satisfy the bandwidth requirements of the workload. And which means that we can remove a lot of the unnecessary infrastructure. We can remove redundant power supplies, we can remove fans, we can oversubscribe internal bandwidth. For the servers, this is the same. We have much less servers in the system than in traditional racks. In fact, we just have enough to have compute for efficient data management instead of having one server every 40 disks or so as in traditional storage racks. So we remove a lot of this unnecessary infrastructure, and we get a lot of benefits in return. Well, first, we have increased storage density because now the space that was occupied by this unnecessary infrastructure can now be filled with additional disks. Second, since this infrastructure is no longer there, the money that was spent on the infrastructure can now be spent on additional storage, which reduces the cost per gigabyte. And finally, since we don't have enough resources for all disks to be active, the performance is capped, which reduces resource consumption and lowers operating costs. So Pelican is a rack-scale appliance for cold data. It's a converged design where power, cooling, mechanical, storage, and software are co-designed for that purpose. It is right provisioned for the cold data workload, which means that we have just enough resources in the rack to satisfy the workload requirements. In particular, it means that we can only have at most 8% of the disks active concurrently in the rack. we have only 2 servers per rack and no top-of-rack switch. And the ingress-egress bandwidth is handled directly by uplinks from the servers to the data center. This allows us to put 1,152 disks in just 52 U, which represents a density of more than 22 disks per U, and is higher than in traditional racks. Our current Pelican prototype, as shown in the picture, stores over 5 petabytes of raw storage. So write provisioning enables us to reduce the total cost of ownership on the system and making it comparable to the cost of tape. But it still allows us to have lower latency than tape. However, write provisioning brings resource limitations that need to be managed in software. And that's what I'm going to talk to you about in the rest of the talk, is how do we efficiently handle these resource limitations in the software stack. So the Pelican storage stack is co-designed with the hardware to handle write provisioning. It expresses resource limitations as constraints over sets of active disks. We classify constraints in hard or soft constraints. If a hard constraint is violated, this leads to temporary or permanent damage to the hardware, whereas if a soft constraint is violated, it only degrades performance. So to give you a concrete example, power is a hard constraint, and if at some point power constraint is violated, a fuse will trip within the rack, leading to 16 disks being unavailable for a period of time, and can even increase the failure rates for these disks because they have not been spun down cleanly. The storage stack runs within the servers in the rack and exposes a blob store API. It has 2 key components that handle write provisioning. First is the placement that determines on which disks each blob should be stored. And the second component is the scheduler that determines in which order requests on these blobs should be serviced. And there are software challenges associated with these components. So for the data placement, we need to maximize the concurrency of requests despite the resource limitations in the system. For the scheduler, we need to minimize the spin-up without sacrificing fairness. There are other challenges associated with write provisioning, but they are handled in the paper. So in the rest of this talk, I'm going to describe you these 2 key components. Write provisioning has a dramatic impact on how resources are distributed in the rack. In a traditional system that is provisioned for peak performance, any disk can be active at any given time. This is not true in a write provision system, in which each disk is part of a domain for each resource, and each domain can only supply a limited amount of resource to the disk that it contains. And a disk can be active only if it has enough resources in all of its domains. So in Pelican, we have domains for power, cooling, vibration, and bandwidth. And to give you an example here, we can see a schematic representation of the rack with a disk D, which is part of a vertical cooling and horizontal power domain. Of course, it is also part of a vibration and bandwidth domains, but here, for simplicity, we're going to only show cooling and power domains. And the resource limitations on these domains are that we can only spin up 2 disks out of 16 per power domain. We can only have 1 out of 12 per cooling domain, and 1 out of 2 per vibration domain. So in that context, the challenge of the data placement is to maximize the concurrency of requests. In Pelican, a blob is erasure coded over a set of disks for data durability. And we enforce that these disks must be made concurrently active for efficient I/O and minimized in-memory buffering on the servers. Now, this is not a big deal if the system was fully provisioned, because in that case, any 2 sets of disks can be made concurrently active, and therefore, the way we select these disks has virtually no impact on the concurrency of the requests. Whereas in the write provision systems, not all the sets of disks can be made concurrently active. It could happen that 2 sets have some of the disks that share a domain and conflict for the resource in that domain. In that case, we cannot concurrently activate these 2 sets of disks. So here we can see that the way we select these sets, basically the placement, has an impact on concurrency. And the challenge in that context is then to form sets that minimize the probability of conflict of two random sets. And this is not so trivial, so I'm going to describe you a simple example to demonstrate that. So if we use a first naive approach, which consists of randomly choosing disks for each blob. So for example, for blob 1, which for simplicity we assume is stored on 3 disks, we randomly select disks that can be made concurrently active in the rack. And the picture also shows the impact on the power and cooling domains that this choice implied. Now, if we want to select disks for a second blob, blob 2, every time we're going to pick a disk, there will be a probability that will end up in conflicting in one of the domains with one of the disks of blob 1. And this probability is in the order of number of disks of blob 1. And since the blob 2 has the same number of disks, eventually, with high probability, we'll unfortunately select a disk which shares a cooling domain with one of the disks of blob 1. And this will lead to a conflict because the cooling domain can only provision cooling for one disk active. And therefore, blob 2 and blob 1 wouldn't be able to be concurrently accessed. So for the random placement, if we store blobs over n disks, the probability that two random blobs will conflict will be in the order of n squared. Pelican achieves much better. It is based on the intuition that it is much better to concentrate all the conflicts over a few sets of disks that are heavily conflicting, leaving the other fully independent. To achieve that, we statically partition disks into groups, such that within a group, all the disks can be made concurrently active. And we ensure the property that for any two random groups, these groups are either fully conflicting or fully independent. And I'm now going to show you how we can form such groups. So here's the schematic representation of the side of the rack. And if we select a disk, it will use one horizontal power and one vertical cooling domain. If we select a second disk along the diagonal, it will use a different set of domains, and therefore it is guaranteed that these two disks can be made concurrently active. And this is, in fact, true for all the disks in the diagonal. We can select 12 disks that share no domains, and therefore, if they're part of the same group, this group is well formed because all the disks can be made concurrently active. And if we repeat the same procedure but one disk down, we can form the green group, which also contains 12 disks, and it is also well formed for the same reasons. But more importantly, these groups, the green group and the black group, fully conflict, meaning that every green disk shares a domain with one of the black disks. And if we take all the rotations of the black diagonal, as shown here, we'll form 12 groups of 12 disks that are fully conflicting. And in Pelican, such a set of fully conflicting groups is called a class. And we can see that the property is verified. Two groups in a class are fully conflicting, but any group within the class is fully independent from the rest of the rack. Now, you may notice that it still shares some of the power domains with disks outside of the class, as shown here in red. However, bear in mind that a power domain has a budget for 2 disks to be active, and therefore this doesn't lead to a conflict. And now, if for the placement we ensure that a blob is stored in one group only, we reduce the probability of conflict to be in the order of n, which is much better than previously. So I showed you an example with groups of size 12, but actually in Pelican, groups are size 24, and we can have 48 such groups. But the same property still applies here. We have 4 classes of 12 fully conflicting groups, and each class is independent, meaning that if we have 2 requests on different classes, they can be processed concurrently. We store a blob over 18 disks within a group, and 18 comes from the 15+3 erasure coding we use. And note that there are slightly more disks in a group than is required to store a blob, 24 versus 18. And we do that because we want to make sure that if some disks fail in the group, we can still find 18 valid disks to write new blobs to it. So all these numbers have not been just randomly chosen. They're a result of a sweet spot in the hardware design and satisfying requirements of the workload. Finally, another nice property of the groups is that groups encapsulate constraints. And by that we mean that at runtime, if we want to determine what blobs can be concurrently accessed, we don't need to worry anymore about low-level constraints on disks. We just need to figure out whether these groups share a class or not. And if we take a group as a unit of scheduling, this simplifies the runtime significantly. So for the scheduling, the challenge is that the spin-up represents the new seek. Each scheduler operates over 12 groups, among which only one can be active at a time. So if we process requests in FIFO order, every other request will have to activate another group, and basically we'll be spending time doing spin-ups. So instead, we use per-group batching with a limited amount of reordering to guarantee that we still have some fairness and requests are not indefinitely delayed. So I just presented you the challenges of write provisioning. The first one is that conflicts in domains reduce concurrency. And we address this by a constraint-aware data placement policy. The second one is that spin-up is the new seek in our system, and we designed an I/O scheduler that amortizes the latency of spin-ups. So in the rest of the talk, I'm going to try to quantify the impact of write provisioning on performance. So the simplest way to evaluate the impact of write provisioning on performance is to compare Pelican to a rack that is fully provisioned and can therefore activate all of its disks concurrently. We call this FP for fully provisioned. Building FP in practice is quite challenging because of the high resource consumption it requires. So instead, in the evaluation, we use a discrete event simulator that we thoroughly cross-validated with the actual Pelican hardware. And in the simulator, we implement both Pelican and FP. In this talk, I will describe you 3 metrics: rack throughput, time to first byte, and power consumption. But more metrics are available in the paper, so please refer to the paper. We use an open loop workload, which is a simple Poisson arrival process with read requests on 1 gig blobs, and we varied the workload rate up to 8 requests per second, at which point all the systems are fully saturated and reject most of the requests. So first, for the cross-validation, we use a burst workload that we first run on the rack and then replay the same sequence of requests in the simulator. And we varied the burst intensity. So here is showing the results for throughput and time to first byte for both the rack and the simulator. And we can see that the simulator is able to accurately predict the performance of the rack for these 2 metrics. But more importantly, it is able to do so for all the metrics we considered. And please refer to the paper for additional results. So from now on, I'm going to only show simulated results. So first, we measured the rack throughput in function of the workload rate. And at first, we implemented this first simple random placement policy I was describing earlier. And we can see that this random placement policy performs very poorly. It achieves no more than 0.7 gigabits per second for any workload rate. And this is because it is not able to handle write provisioning. And this perfectly illustrates the fact that write provisioning can ruin performance if it's not well handled by the storage stack. The performance of FP, which is only bottlenecked on the egress bandwidth, is much higher. And at a workload rate of 5 requests per second, it actually manages to saturate the egress bandwidth. Now let's have a look at Pelican. And here we can see that Pelican is able to much more accurately handle write provisioning. In fact, for workload rates up to 4 requests per second, Pelican achieves the same throughput as FP. And that's regardless of the fact that only 8% of the disks in Pelican are active, whereas in FP, all of them are active. Beyond that point, for more intensive workloads, Pelican plateaus at 32 gigabits per second. And this happens because despite all the optimizations, Pelican, by design, has to spin up disks. And the overhead of doing that is captured by the metric and appears here. However, bear in mind that we can configure the scheduler to trade off more fairness to achieve higher throughput. And therefore, for very intensive workloads, we can achieve even closer performance to FP. So, right provisioning, we can handle and achieve very good throughput. Now, what about latency? Well, this is the takeaway thing here is that by design in Pelican, we need to spin up, activate groups to service requests. And therefore, there will be a lower bound on the time to first byte, which is the time that it is required to activate a group in average. And we measured this time in our evaluation, and it is in average 14.2 seconds. This encompasses the time to spin up all the disks in the group and mount their file system and perform various checks on the file systems. So for low workload rates, that's the time to first byte that Pelican achieves. Of course, FP doesn't need to spin up disks, and therefore offers much lower latency. However, this comes at a great cost of having all the disks active in the rack. So we now evaluate that. We measure the aggregate disk power draw in kilowatts in function of the workload rate. First, this is the consumption for all the disks spun down, 1.8 kilowatts. And this, it still consumes some power with all the disks spun down, because when disks are spun down in standby mode, the electronics of the disks are still operating. So here is the power draw for all disks active. And that's what, by the way, FP would consume. So this is really high. And if we look at Pelican, in average, it achieves a power draw much closer to all disks standby, all disks spun down, than all disks active. And we can see how the power draw evolves with the workload, because it is a function of how many disks in average are active, spinning up, or spun down. But even for peak performance, we can see that the power draw is effectively capped and is lower more than 3 times compared to FP. So to conclude, I presented our Exascale hardware-software co-design for cold data workloads. It's composed of an efficient hardware which is right provisioning for the requirements of the cold data workloads, and a software stack that is able to efficiently manage constraints that result from that. We have a proof of concept prototype rack that stores over 5 petabytes of raw data in just 52U. From the design of Pelican, we learned that handling so many constraints while designing the system is really challenging to do manually. And furthermore, these constraints are a function of the hardware. And therefore, if hardware evolves, we need to change the constraints and possibly adapt the storage stack. So this led us to our follow-up work, which is called Flamingo, and is a tool to synthesize cold storage stack for Pelican-like systems. We have a poster in tonight's session, so please come to see it. Thank you.
We have time for probably one question.
Good thing I got here first then. So you referenced the MADE work that my thesis advisor published in 2002. Were you aware that there was a startup that was based on that produced a product for 8 years, that the assets of which were bought by SGI in 2010, called Copan Systems?
So we are aware of the MADE work, and
the MADE work was just a 2-page long work-in-progress talk at a conference. The startup actually built a product that looks very similar to what you are presenting.
All right, we can discuss that offline, but we believe that what is unique in the system is that we have some requirements for our cold data workload, and we write provision both the hardware and the software stack for that requirements.
Yeah, I'll come talk to you.
Yeah, thank you.
First of all, Robert Escriva from Cornell University. First of all, very nice work. I have a question about spinning up and down the disks. Most disks still die after about 500,000, 600,000 cycles. which means you can spin them up and down 1,200, 1,500 times a day. So if you're putting stuff in cold storage for a year and a half, the disks that hold the data could actually start dying before you actually start needing to read the data off. Are you assuming that disks are going to get better at this, or do you have some plan?
So the disks we use are archival ones that are specifically optimized for spin up and spin down cycles. And
Like how many cycles can they handle?
so that's in the spec of the archival drives that is unfortunately confidential. But from personal discussions with the hardware designers of the disks, they ensure that it should be manageable. I mean, they're specifically designed for that.
Okay, thank you.
Right, thank you.